There, that's better. Now, can you hear me? I don't know where the feedback's coming from. Oop, now I do. I think I fixed it. All right. We'll give it a second for more people to log on. All right, I guess I'm going to go ahead and start, even though there's only a couple of us here. I am actually recording this week, so I'll put the video out when we're done, and people can watch it. But what I'd like to do is start off with the with the chip formation that we looked at a couple weeks ago in class, and just start off with this YouTube video. And so again, the chips forming on that rake face of the tool that feeds across the part. And you can see here the workpiece is coming down. That's our uncut chip thickness. Then it feeds out across that rake face of the part. And because of the material here, it's all curling up like that. And it matches the model that we draw when we're modeling this orthogonal cutting. And here our rake angle is 0. And for this part, our side edge cutting angle was also 0. But so I want to show you how you can see this yourself without having to be in the machine shop, in this sort of a simple experiment that you can do on your kitchen table to observe this chip formation and see how changing things like that rake angle can affect the way that you're making the chips. And so I'm going to switch computers. I'm going to unmute. Turn off the other speakers so we don't get an echo or feedback. All right. And so what I've got set up here is I'm using a vise, and I've got a lathe tool holder, and I've got some models, but I'm going to show you how you can do this without all the fancy equipment also. We'll go ahead and switch cameras. And you should see a view of my right shoulder, sort of the bottom of my chin, and a vise with the cutting tool on it. Is that what you guys see? Oh, I'm going to stop the screen share. Did anyone hear me?
Yes.
Can anybody hear me?
Yeah, you're all set. I hear you.
All right. Now let me get the. I don't know why there's an echo. I'm going to log this one off. All right. Can you guys hear me? Can somebody speak up?
Yes, I hear you.
All right, perfect. Thanks. I tried to be ready because I'm going to walk out in the lab in a few minutes. So I had my phone logged in, and I had two computers logged in, and apparently that was too much. But you should see a vise, my right shoulder and hand. Is that in the view that you guys can see now?
Mm-hmm.
Okay, perfect. All right, so I've got my workpiece material here. Oh, I need to grab a vise. Give me a second. All right, now I think I'm ready. So I'm going to open the vise. I take my workpiece and mount it in the vise. Now I have these cool 3D printed fixtures that I made for doing this, but you don't need them to practice this at home. All right, so you can see we've got a workpiece, we've got our cutting tool. If I put the cutting tool like this, And I'm going to move it across the workpiece in this direction. So because of the way I've got this set up, I'm technically feeding across the workpiece, but in reality, in the turning exercise, all of this kind of motion comes from the workpiece rotating down to the tool. And so instead of doing a turning operation here, I'm doing a planing operation. The way the cutting forces work and the way the chip formation works, the physics of the two operations are identical. And so I've got my cutting tool, and I'm going to come, I've got an initial depth of cut. So I've got this, this T1, this initial chip thickness. I'm going to move across. And you see the chip form on the edge of the cutting tool. Now I'm doing this, a second. Chips are good. Okay. So now I've still got the same workpiece. I've got a new cutting tool. And so I'm going to see if I can make a chip across the top of the workpiece. And so my depth of cut went down a little bit as I went across there. That was because the first tool tended to dig in and I didn't have a smooth surface. Okay. And so that is with a rake angle of 0. Let's see if we can see any difference if I have this positive rake angle. So did you see a difference in the chip formation there? The chips are good. At that edge. So who's ever done this experiment before at home? Without knowing that you were doing an experiment? Anybody?
I mean, I haven't with butter, but maybe like using a knife, a pocket knife in wood.
Sure. And so there's two ways that you cut butter at home, right? You cut it like this when you want a big honking slab to put on your piece of toast, and when the butter is soft. But if the butter is really hard, like it just took out of the freezer, it's really difficult to cut it by just coming straight down with the knife, right? So when the butter's really hard, you come across the top like this. To get enough butter so you can put it on your toast, or if you're like me, you just like to eat it. That's the exact same process as when the cutting tool is coming through the workpiece material. Now, because of the way this tool is set up, you see the edges, and there's a big groove right there where the cutting edge is. I'm not sure how clear it is in the video. And what that does is it effectively gives it a very positive rake angle at that location. And then as the chip goes across the rake face of the tool, it gets bent back when that top of the tool changes. That feature on the tool is called a chip breaker. And the chip breaker is there in order to make those chips curl back up on themselves. A more brittle material than butter, which is what our workpiece material is here. A more brittle material wouldn't curl up like that. It would break off when the chips got curly. And you'll see that if you're using in a lathe, if you're using a tool like this with a chip breaker, as long as you have a high enough feed rate and a high enough incremental depth, the chips curl up and they break off. So I want to encourage you that if you have some time, next time you're having toast, to experiment a little bit with different techniques of cutting the butter and to see if you can see how the chips form on the edge of your cutting tool while you're doing that. And that's just kind of a simple thing that you can do at home to try to visualize the things that we're focusing on in the lab. The other thing I wanted to do today, though, is I wanted to go through at the lathe one of the lab exercises that we're doing in lab this week, and to shoot that live with you. So give me about 3 minutes to get out to the lathe and to get logged back into the Zoom call from my phone, so we can do that live from there. And I'll be back. All right, now I think you should be able to see the things that I see. Can you guys hear me?
Yes.
Perfect. All right, so in this lab, what we're doing is we're really practicing setting. Can I have you pause while I'm doing this? One of the problems with the instruction in the lab is that there's other machines running. So I've just asked someone to pause their program while we go through this. But all right. So what the purpose of this lab exercise is to actually practice telling the lathe how long the tools are and where they're positioned. So we're setting the tool offsets in the lathe. At the end of it, if we do it right, we're actually going to make a little snowman that you can take home. And it's really not that hard to do. I'm going to change the focus over here. First, what we have to do is we've got to have our program. So I'm going to go to the memory mode and open up the program. And as I do that, so you can see, I don't know if you can read that or not, but at the top of the program here, there's a list of the tools that our program uses. And so it uses tool 6, and it uses tool 10. So those are the only two tools that my program uses. What I'm going to do is I'm going to pull out the stock material so that it's far enough out to make the part. When I look at the lab instructions for this lab, it says They say to pull out the stock material 2 3/4 inches. And so we can operate the chuck on the lathe. We want to pull out our stock material, and we want to measure that. So I'm going to measure it with this square and ruler. I'm going to set this to 2 3/4 inch. And I set it just a little bit past that. And then I can hold my ruler up on the part, and I want to push it up to the point of the chuck here that's furthest out, the closest to the turret. So I've got it out at 2 3/4 inch. And I step on the foot pedal to close the chuck jaws. And then I want to double check that I've measured that correctly. So I got 2 3/4 inch, maybe just a hair past that. So I've got my stock material out. Our program uses only 2 tools. And so what I'm going to do is I'm going to tell the machine tool where the end of the stock material is with each tool. And I'm going to set the tool offsets that way. And so our program uses tool 6. Close the door to do a tool change. T6 forward. All right, so tool 6 is in the cutting position. And with the handle jog mode, I'm going to jog over so that tool 6 is in front of the workpiece, but not touching it. So it's in front of the workpiece, but not touching it. And next I'm going to take this dowel pin. And so I know that this dowel pin is 5/8 of an inch. So it's 0.625 inches. To make sure it's clean, doesn't have any debris on it. And I'm going to try to fit the dowel pin between the tool and the face of the part, and it doesn't fit. So I'm going to take the dowel pin out, and I'm going to jog a little bit away. And then I'm going to try again to fit the dowel pin between the tool and the face of the part, and it doesn't fit. So I'm going to jog away again. And I'm going to try to fit the dowel pin between the face, and it doesn't fit. So I'm going to jog a little bit away. And I iterate this until the dowel pin fits. And so now the dowel pin fits between the face of the part and the tool. I take the dowel pin out and come closer by 1 click and see if it fits. And it still fits. So I'm going to come 1 more click, but I'm never jogging towards the workpiece with the dowel pin in between the tool and the workpiece. So now it just barely fits. I can feel it touching. I'm going to do 1 more click. And now it just doesn't fit. On the controller, when we're jogging, we can set how fast we want it to move or how far we want it to move for each click. And so right next to the handle jog button here, this will move 1/10,000th of an inch for each click. This will move 1,000th of an inch for each click. This will move 10,000ths. This is the setting that we were on. So I'm going to move it to the setting that's 1 smaller than that. Come back in the lathe. And so now my dowel pin does not fit. I'm going to jog away 1 click at a time until it does. And you notice every time I'm clicking, I'm moving the dowel pin out from the space in between. so that if I accidentally go the wrong direction, I don't jog towards the dowel pin. And so now it just barely fits. So that means the tool is within 1/1000th of an inch of the diameter of the dowel pin away from the face of the part. Now I can get it to within 10 thousandths by repeating that with the 10,000th. And so now the tool is within 1/10,000th of an inch away from the dowel pin diameter from the face of the part. And so what I'm going to do is I'm going to go over here to the offsets page on the controller. And so I'll hit the offset button until the screen says that the tool offsets are highlighted. This is tool 6, and I'm setting the Z offset. So I want the Z offset to be highlighted, and I can press the Z face measure button. And when I do that, it tells the machine that where the tool is right now is where the end of the workpiece is. Now I could subtract the diameter of the dowel pin. And to do that, I just make sure that I have the offset that I want highlighted here on the screen. And on the numeric keypad, I just do minus 0.625. Enter. And yes, I want to do that. And it subtracts the value that is stored in the offsets register in the controller. Now the other tool that we're using is tool 10. I'm gonna close the door, go back to the home position so I can change tools. And again, just like in the mill, I tell it the tool number, I want tool 10. I make sure I'm in the MDI mode, and I do turret forward or turret reverse. And it changes to tool 10. Now I'm going to handle jog tool 10 over next to the part. And so tool 10 if you can see it, tool 10 is a cutoff tool or a deep grooving tool. And the way we write our programs here at WPI is we always program the edge of the grooving tool to be the part that touches the finished part. And so I could do the same method with my dowel pin, jog over until I can, or jog over and then jog away until I can slide the dowel pin in. Or I can take a little shortcut. I'm going to go in Z until I'm past the end of the part. Come down in X until I'm close, maybe 1/4 of an inch away. And I can take a straight edge. So I can take a straight edge like the one that we used to measure the part. And I'm going to hold it on the face, sticking past it. And then I'm going to slowly jog in Z until I feel the edge of the tool touch my straight edge. And so it's just touching. I can now go back over here to my offsets. Make sure that we're on offsets, we're on Z. We're on Z, it's tool 10. I'm going to go ahead and say Z face measure. And I don't have to subtract anything because the edge of the tool is right where I want it to know the end of the part is. Now, if we use this method where we're setting the tools off the face of the workpiece, we want to make sure that the work offset, cycle between tool and work offsets with the offset button. I want to make sure that the work offset for G54 is 0. And that way it knows that all the tools are measured from the end of the workpiece. The next thing we would do is we would go through, once we've set the offsets, it closes the door. I'm going to send the machine to its home position. Next thing we want to do is go to memory and setting graphics. We press that graphics button twice so that we can get to the graphics screen. And if I do cycle start now, it will run a simulation of the program. And so the tool came down, it roughed away this material, it went around there, and then there was a cutoff operation. And so my simulation looks okay. I know that, let's see, and before I run the program, I'm going to come back over here to the computer. I'm going to make sure that I go to MFE Labs, WPI Manufacturing Labs, screen bigger. I want to do a safe operation checklist. And so this is me. And we started, let's call it 11 o'clock. And this is lathe number 1. This is for ME1800, Snowman. And so we don't need to worry about this. We simulated in the CAM software. I did that before I came out. I set the tool offsets. I set the work offset to 0. I simulated on the controller. I'm reducing the rapid rate to 25%. And then for each tool as it comes out, we're going to stop and we're going to check the distance to go. And so let's see if I can get a good view here. Through the window. We go ahead, 25% rapid, current commands. And cycle start. First thing it does is change to the tool 6. It comes over, it comes down. I'm going to slow it down to 5% rapid. Let it come down. And so it's almost touching. I'm looking inside and it looks like it's about a ½ an inch away from the edge of the part. And I look at my program and it says the line it's on is going to move to the value x equals 1.37. But I know that all the x's in these programs are in diameter. So I believe that it's going to go a little bit in x there, about, so take this number, divide it by 2, so about 18 thou, or 180 thou. And it's not going to touch the part yet. So I believe that. So I think I've set that correctly. I'm going to go ahead and cycle start. And this is the problem with lathe programs, is it's really hard to see what's going on inside when the coolant gets sprayed all over the so it's doing the roughing passes now.
It looks like it's made a little top hat. It's got the head of the snowman and the body coming out now. We're going to go back to 25% rapid. And I'm going to stop this again. I'm actually going to stop the spindle. And I'm going to open the door. Because the tool is pretty close. You can see the tool is pretty close to where the chuck is. And I want to make sure that I'm not going to cut the chuck when it comes in. So I've stopped the program with feed hold. And I've stopped the spindle just by manually pressing the stop button. And I just want to double check here before we get to where the chuck jaws are that my tool is not going to hit the chuck jaws. And so you can see that we're probably about a quarter of an inch away from the chuck jaws. So it's going to be safe for that tool to feed in and cut off the workpiece. So again, close the door again. Go over here to my override controls, and I'm going to press forward to start the spindle again. And then once the spindle's started, I can hit cycle start to restart the program. And you can't see much here with the coolant. And so that is our snowman here. One of the things you'll note is that the part has this little nub on the end of it here. And that happens because as the cutoff tool is coming in, here, eventually the cutting force is more than the strength of the material and the part just breaks off. And so we'll typically take care of that with put the part in a vise and file it off. Often we'll have another operation where we hold it in the lathe and we machine it off, or you can even sometimes just break them off with a pair of pliers. There's a little stringy chip all tangled up like a scarf. And so I'm just very carefully pulling that off of there. You have to be really careful though when you deal with these chips because they're very sharp. All right, so that's our snowman part. Let me go back in the office real quick. Before I walk away, I'm going to hit the emergency stop. And you're good to start. Thanks. No, I didn't just hurdle that. I only lifted up the camera. All right, I'm going to log off on the camera, on the phone.
All right, I should have just one microphone turned on now. And so the important things about I don't just have one audio source turned on.
I think you're muted on the other audio source. The icon has the no mic icon.
It is kind of weird because I hear an echo. Oh, I just needed to mute the speakers. I needed to mute the speakers on the other. device. That was the problem. All right, now I can turn these speakers on. All right, now it should work. So yesterday in lab, no, Patrick, that wasn't a program. That's from one of our CAM assignments. We had originally planned to add another part to the Stirling engine. And so we had scheduled this time this week to be making that new part that we were going to add to the Stirling engine. We were going to add a little alcohol burner to it. We didn't finish designing that before it was time to start the term. And so I had the PLAs vote what program we should run this week since we didn't have that Stirling engine part to make. And they voted for the Snowman. I hope they're optimistically thinking that this will put off into the future when it's going to start snowing here in Worcester, but who knows? Could snow tomorrow.
I was mainly talking about like the format of the file. Like I
The
know
format, yeah, absolutely.
Okay, cool. So when we make
program
that
was written in a
file,
spree.
okay.
Yeah, so the program was written in a spree, and the post processor that we use here, it always puts out the tool numbers at the top of the program for the lathe programs, and it makes it really easy when you get there to make sure that you know what tool you're supposed to use, especially if you're using code that's on the machine. So if somebody else made the code,
Is that like a machine specific thing, or is that just like a general language?
they are they're machine tool brand specific, and sometimes machine tool model specific. So some machine models may have different commands than other ones do, but a machine tool maker will typically be standard across their own models.
Hmm.
And it's almost standard across the industry. There are some differences. So the code M0, so the code M03, for example, on all the Haas machines, on all the lathes, the code M03 tells it to spin the spindle clockwise. On some FANUC controls, I've seen M03 be the command to spin the spindle counterclockwise. And clockwise and counterclockwise makes a big difference when you're installing the tools in the machine. Okay. We've actually had that problem where we downloaded. So the thing that translates it from the CAM software to the G code that runs on the machine is called the post processor. Yeah. And it's built into the CAM software, but you can have different files depending on which machine tool you're using. And so there was when we got a new Haas lathe one time, we downloaded a new post processor that was supposedly written for that lathe. But what somebody had done is they had taken a FANUC post processor and modified it to work for the Haas lathe. They hadn't fixed they were posting M04 to spin the spindle clockwise instead of M03. And in the Haas control, M04 spins the spindle counterclockwise. And so the first parts that we cut came out, instead of cutting, we were forming the metal with the back of the tool, basically. But since the spindle on that lathe had 30 horsepower, it still made the part. It just looked funny. But the thing that's really important about this manually setting those lathe tool offsets or the mill offsets, when you manually set the mill offsets, is you never want to jog the tool towards the workpiece when it's close enough that it could touch the workpiece. And so that's why every time when I was jogging forward, I took the dowel pin away so that if I jogged further than I meant to, I wouldn't run into the dowel pin and break the tool. Those tools do a great job cutting when the workpiece is spinning. They do not cut when you just drive into the workpiece. And every time, if you drive the tool into the face of the workpiece or into the dowel pin, it breaks the tool. And so that's sort of critical there. And then the thing with the cutoff tool, since I knew that I wanted to set to that edge, what I could do is I could use the same dowel pin trick and set the cutoff tool and then subtract the thickness of the cutoff tool, but having measured it. But I find it's a lot easier to go past the part and come back and know when I'm lined up. And it really depends on how much precision do you need. Often with the lathe parts, you set it up quick. I want to say quickly. You set it up quickly, maybe using little shortcuts like I did, where I went past it and came back. And you make a part, and then you measure that part and see, does the part conform with my specifications? And if it does, you're good to go. If it doesn't, you can adjust the offsets relative to each other a little bit so that you can make it cut the part. So if it's two different tools and they didn't interact correctly, you can set offsets differently. The other thing is we didn't look at the diameter offset when we did that. We were just looking at the Z offset, mostly because for the snowman, I really don't care what the diameters were. But when we do the cylinder and the piston, getting those diameters correct is critical. And so we almost always have to set it up so that we get it as close as we think we can. And we cut a part. And if the part is too big, we can change the tool offset to make the next part be smaller. And if the part's too small, we can change the tool offset to make the next part be bigger. And that just takes some practice. And when you guys get back on campus, you'll have plenty of opportunities to do that. I'm happy to have you come in and make all of the ME1800 parts if you want to. Even join an ME1800 lab group if it's not oversubscribed when you get back to get the rest of that. For the lab practical exam, what we're going to be doing, and you can get the information you need from the CNC Quick Guide, which we had you download the first week, I think, or get access to. That's lead instructions. If you go to cncquickguide.com, let me just quickly share the screen here. So you go to cncquickguide.com, and the lab practical exam is always on the mills. What we're doing is we want to make sure in the in-lab practical that people can do the steps listed on the checklist. So can you set the tool offsets? Can you set the work offsets? Can you simulate in the CAM software? Can you simulate in the controller? And do you know, do you reduce the rapid rate? Do you check the distance to go? So in the lab exercise, we watch people do these steps. We give them a very simple part. It uses one tool. We say, set this part up in the machine and cut it. And if they go through and they check all the boxes, they get 100%. If they know they need to set the work offsets, but they don't know how, and they ask the PLA, how do I set this work offset? The PLA tells them, and they take off 25%. So if you ask how to do something, you still get to do it. No, if you ask the question, you take off 5%. If you skip a step and don't do it, then it's 25%. So the idea is that when you get to the edge of your knowledge and you go ask for help. So you could ask how to do all of the steps and still pass the exam. What we're going to do on the lab practical online version, and I'm going to have everybody in the class take the online version. What we're going to do there is we're going to have people demonstrate that they understand why we do each of these steps. So if you understand why you need to do these steps, and you can get that, it pretty much says it in sentences underneath the check marks here. And we'll ask a little bit about how to do it. We've got some questions where we give you a diagram of what it looks like in the machine, and you're on the check distance to go step, and you say, should I stop the program, or should I click cycle start to continue machining? And so it's using your judgment there. And those, if you understand why we're checking the distance to go and how to do it, which you can find, table of contents, program operations, check distance to go. So you can read about how to check distance to go over here. You don't have the chance to have experience doing it, but I think it's clear enough. And again, that we're going to put that out just like all the other quizzes, where if you get it wrong, you have a chance to go back and do it again. So my goal is to have all the quizzes. In fact, I had wanted to stop calling them quizzes. I want to call them homeworks because I want them to be a learning experience for people doing it, not just a testing experience. So we have to have some metrics so we can assign grades. But the important part of it to me is the learning, not the assigning grades part. So I don't know. Do we want to meet next week at this time and go through testing Stirling engines, setting them up, assembling them, and trying them? Or do you guys want to not meet next week at this time?
That would be just putting it together from
It's just putting it
Kit Bot.
together and playing around, seeing if it works.
Yeah, I'm fine with
What
that.
we're doing next week in lab, except, I mean, so if you're not doing your lab practical, you're going to be assembling your Stirling engine.
Yeah,
Is
fine
the
with that.
idea with the lab practical that if you've been on campus and you've been like doing all the labs, you're going to get 100?
The purpose of all of the in-person labs are to make you comfortable enough using the machine that you can easily do the lab practical.
Okay.
So that's it's really about, and I think one of the hardest things people have when they're first learning CNC machining is learning to be comfortable with the machine and having confidence that when they press a certain button, it's going to make the machine do a certain thing. And you get that confidence and that comfort level by practicing. And so the purpose, and once somebody has passed the lab practical, they're free to use those machines anytime they want to. So it's also the qualifier. So if you want to come in and use a mini mill, if you've passed the ME1800 lab practical, you can use the mini mill. You don't have to ask permission first. So that's the other purpose of it. So it's just a practical check. And again, you can pass the lab practical by asking how to do each step. So as long as you know you don't know how to do it, you can still pass the exam. And I encourage you when you get back on campus to come in and just say, hey, I want to get checked out on a mini mill, or I want to get some practice so that I can get checked out on a mini mill. We always have, there's always open lab hours on Fridays and Mondays. Fridays, Mondays, and usually Wednesdays, there's open lab hours, and there's either staff or PLAs that are around to help people that just want to learn. My goal, so we can play it by ear, or maybe I'll be available on Wednesday at this time next week anyway, if people want to come on and talk about assembling the Stirling engine, or if you've had trouble, you want to ask about it. If people don't want to, then we'll see you next term when you're back on campus, or 2 terms, or whenever. Anybody think we're going to be back on campus C-term?
C-term? I think C-term probably.
You think C-term is going to be normal operations? I don't think so.
I don't think it's going to be
so.
normal. I just think more people are going to be
distanced.
back. Yeah, no. I just think more people are going to be back.
Yeah, so I teach 2 classes in C-term. I teach A1800 again, and then I have another class, 3820, which is typically about 20 students. And so I'm trying to decide, I think I'm going to have the small class try to be in a classroom. Because you do miss something. I love Zoom, but you certainly miss that person-to-person interaction, especially at 8 o'clock in the morning when everybody's in bed.
One thing I'm not looking forward to about C-term is my IQP is probably gonna have to be remote, so that's not fun.
I heard last year about it was mostly MQPs that were remote last year. I guess there was some IQPs too in D-term. And I heard from the advisors that they all worked out great and it was perfect. And I also heard from students that said it may have worked out great, but it was really hard.
Yeah, I mean, like I would be going to Thailand if it could work out, but I get all the benefit of working with the team on an 11-hour time distance with none of the going to Thailand.
Hey, but that's like life as an engineer too.
Really? Okay.
I mean, my wife regularly works with people in Asia and in Europe.
That's fun. Is that you guys own a machining?
We own a machine shop and actually a small software company. But she works at Johnson & Johnson. She makes knee implants. She's a senior scientist at Johnson & Johnson.
Wow. You guys do a lot.
Yeah, oh, and we have 2 little girls.
Nice.
So, but Zig Ziglar, I don't know if you guys follow any of these personal development speakers, but Zig Ziglar is famous for saying that if you do the things you have to do when you have to do them, you'll be able to do the things you want to do when you want to do them. And so that's sort of our plan. And I'm shopping for a bigger boat.
Are you hunting a shark?
What's that?
Are you hunting a shark?
No. No. As soon as the kids go to college, I'm moving on to a boat.
Like a houseboat or just like
Sailboat.
Oh, okay.
So yeah, it'll be my home though, so it's like a houseboat.
It's a boat house.
Boathouse, yeah. So, but it's been fun. We've gone over the time, but thank you guys for being here. And I'll log on next Wednesday at the time. Don't feel obligated to unless you want to.
Have a nice one.
You too.
Professor, I have a quick question if you don't mind.
Go ahead.
So this is about the camp assignments.
Okay.
So I kind of messed up my Camp 4 assignment.
That's no problem.
And-
You can do it again.
Okay, that's what I was gonna ask you if we could still do
Yeah,
that.
I actually, I'm not sure if it was clear when I was talking to the class earlier this week or last week, but I'm not gonna take off points for any assignments being late. And the camp assignments are multiple attempts. They should be all set for unlimited attempts. Please don't resubmit all of them on the last day of the term.
Okay.
Because I will grade them all again, and don't resubmit it like 14 times. So before you resubmit it, you can set up a time on my calendar or something. I can go through it with you to make sure that it's correct. And then you won't even need to submit it. I can just change the grade.
Awesome. Okay.
Yeah, we're actually trying to figure out a better way to do that cam grading, because the only reason it takes a long time to grade it is because whoever the grader is has to download it, open it up, check a bunch of the settings, then make the judgment about it, then type in the response, and then move on to the next one. And that takes, it takes like 10 to 15 minutes per person, which doesn't sound so bad until you think of the fact that there's 70 people.
Jeez.
And you get tired of doing that pretty quick when you're doing it. And honestly, if you had it open on your computer when you thought you were ready, and you could press a button and say, hey, can you look at this? And you run the simulation, we ask you some questions, we could judge immediately whether or not you understood. And you would get instant feedback. So we're trying to change the grading system to be something like that, where, basically, if you get instant feedback, then you can learn faster. And if you have to wait, then there's really no learning to the grade assignment. So,
okay. Yeah, that makes sense.
so yeah. And also we have, although we have more PLA tasks this year because of all the budget uncertainty at WPI, our budget for hiring PLAs is 50% of what it nominally is. And so we used to have PLAs do the grading, and it was the PLAs that were working your lab section. So you knew the people that were doing the grading, and it was a lot easier to get iterative feedback then. And since we had to cut something, we cut the grading from the PLAs because we wanted to still have the contact in lab.
Oh, okay.
So yeah, so we'll blame the economy.
All right.
But no, I think there's got to be ways. Plus, the more I have to do it, the more I want to make it better and automated, because they say that the lazy people are the best inventors. I'm looking for methods to make the grading easier and more instantaneous.
Yeah, that makes sense.
Yeah.
All right. Well, thank you.
And I had a staff member doing a bunch of grading, and I thought he was grading them one at a time and putting them in Canvas, but he was waiting until he was done with all of them before he uploaded the grades. So once we figured out that miscommunication, 2 of them were instantly graded.
Oh, okay. That's funny.
Because he was just waiting so he could go back on Canvas and upload everything at once.
Jeez.
But we all learn.
Yeah.
I'll see you guys in class. I guess we got Monday next week, right? Is that
Yes.
the last lecture on the schedule?
Well, I think it's Tuesday, I believe.
Or Tuesday, yeah, whatever. The first day of the week that we have lecture.
Yeah, pretty much.
That might be the last one on the schedule.
Oh, really?
Yeah, I usually don't do one at the end of the week 7 because people have exams and stuff like that.
Oh, okay.
All right. Well, I'll see you guys.
All right, awesome. Thank you.
Bye.
Thank you, Professor.
Thanks. And thanks for making this work long distance.
Yeah, of course, no problem.
Thanks, Professor.